Continuing with the Professor Lewin series of lecture videos on fundamentally electrical and magnetic phenomenon. And I guess we're on video 4, which makes this video 7, something like that. Anyway, probably going to start getting into mathematics, and I may speed the video up for that, but we'll see how it goes. Also, I did do an overview style video on the subject of the one force of magnoelectricity or whatever, and how I think it fundamentally functions, and why it's, I think, reasonable to understand that there is only one force. There's not a separate kind of force for magnetism and electricity. It's the same mechanism, both, just different atomic interpretations. Pressure versus polarization. So leave us continue. So I'll link below to that video as a supplement. Yeah, pretty much. And so
we're going to talk about, again, some new concepts. And that's the concept of electrostatic, potential, electrostatic, potential energy, for which we will use the symbol U, and independently, electric potential, which is very different, for which we will use the symbol V.
So potential energy is kind of a tricky word. Obviously, when you create pressure, you can depressurize. A lack of pressure, you can pressurize, but it's going to take you energy to do that. So the idea would be is anytime you pressurize a system, you impose potential energy. And then electrical potential is just a way of saying electrical pressure would probably be a better way to say it. But again, it's as soon as I say the word pressure, I've said the word potential. So that's probably good shorthand.
Imagine that I have a charge Q1 here, and that's plus charge. And here I have a charge plus Q2, and they have a distance r apart, and that is point P. It's very clear that in order to bring these charges at this distance from each other, I have to do work to bring them there, because they repel each other. It's like pushing in a spring. If you release the spring, you get the energy back. If they were connected with a little string, the string would be stretched. Take scissors, cut the...
Right, so we sort of said it the wrong way. If it was string, you'd stretch it. He's really just talking about two like charges, and the fact that the real word for phenomenon is the like charges repel, and it takes energy to push like two same magnets together. Is the most easy metaphor. And so I would just point out that that's perfectly consistent with the fact that there's something between them. It could be as simple as a ping pong ball kind of thing to understand. And as you bring them closer and closer, that thing, moving at constant speed, would impact the surfaces more and more often per second, which could be easily understood as pressure. And so he's basically talking about how to calculate that pressure, I imagine.
String, they fly apart again. So I have put work in there, and that's what we call electrostatic potential energy. So let's work this out in some detail, how much work I have to do.
So mechanic work. You could argue that that's sort of what happens with the Earth. It gets compressed, and if all of a sudden you could eliminate the force of gravity, it would spring back.
Well, we first put Q1 here. If space is empty, this doesn't take any work to place Q1 here. But now I come from very far away. We always think of it as infinitely far away. Of course, that's a little bit exaggerated.
Right, so they have to grab all of what it's going to take. So you're trying to figure out what's the total amount of force. Nobody would ever need to know that. They only need to know it from a position to a position. Because in the real world, you know, yes, you're not going to go, no infinite systems.
And we bring this charge Q2 from infinity to that point P. And I, Walter Lewin, have to do work. I have to push and push and push. And the closer I get, the harder I have to push. And finally I reach that point P. Suppose I am here.
All right, so another way to think about it is undoing pressure would be the same thing. And, I mean, undoing pressure that's in the opposite direction. And so you could think that it's just about calculating how much energy it would take to get free of gravity. You know, to get to a point where the gravity is insignificant. And you could calculate that work.
And this separation is little r. I've reached that point. Then the force on me, the electric force, is outwards. And so I have to overcome that force. And so my force, F Walter Lewin, is in this direction. And so you can see I do positive work. The force and the direction in which I'm moving are in the same direction. I do positive work.
So you overcome gravity, you do positive work.
Now, the work that I do can be calculated. The work that Walter Lewin is doing, in going all the way from infinity to that location P, is the integral going from infinity to radius r.
So that's the same as like calculating, because gravity goes forever, calculating every single bit of gravity that the Earth is producing. So obviously you know that as soon as you get to just moderate distances away from the Earth, you've already done 99% of the work and there's only 1% left.
Of the force of Walter Lewin dot dr. But of course, that work is exactly the same, either one is fine, to take the electric force in going from r to infinity dot dr. Because the force, the electric force and Walter Lewin's force are the same in magnitude but opposite direction. And so by flipping over, going from infinity to r to infinity, it is the same. It's one and the same thing.
So yes, the gravity, you consume so much gravity to create the pressure of gravity, to create the pressure of gravity, and it's so the same amount of work would to overcome it. Plus, if you want to overcome it, you got to add some though. So if you want to escape gravity, you have to do gravity, the G force. But if that's all you do, then you just stay in one place. You don't go anywhere. So you have to do gravity plus the force to escape. And escape is basically a time equation. So I don't know, it doesn't have any time equations in here yet.
Let's calculate this integral, because that's a little easy. We know what the electric force is. Coulomb's law. It's repelling. So the force and the r are now in the same direction. So the angle theta between them is 0. So the cosine of theta is 1. So we can forget about all the vectors. And so we would get then that this equals q1, q2, divided by 4 pi epsilon 0. And now I have downstairs here an r squared. And so I have the integral now, dr divided by r squared, from capital R to infinity.
So 4 pi epsilon 0 equals r squared? No, that's not right. Oh, that's an added integral. Okay. Still nothing timey in there.
And this integral is minus 1 over r, which I have to evaluate between r and infinity. And when I do that, that becomes plus 1 over capital R. Right? The integral of the r over r squared, I'm sure you can all do that, is minus 1 over r. I evaluate it between r and infinity, and so you get plus 1 over r. And so U, which is the energy, that the work that I have to do to bring this charge at that position, that U is now Q1 times Q2 divided by 4 pi epsilon 0 divided by that capital R. And this, of course, is a scalar, it is work, it's a number of joules.
Alright, so he's just calculating it as if it was a perfect world where you didn't count the fact that the force continues to hit you and push on you. So he's just thinking of it in some perfect world where time is irrelevant and you're just overcoming the force that exists at one moment in time. not the force that will be continual, which I don't know where that would be useful, but fine.
If Q1 and Q2 are both positive or both negative, I do positive work. You can see that. Minus times minus is plus, because then they repel each other. If one is positive and the other is negative, then I do negative work. And you can see that that comes out as a sign set.
Right, it would be just kind of retarded because the charge would be pulling you. So if you didn't try to force it, it's going to pull because it's attractive. So, but what's really happening is the external force is pushing because you've eliminated force in between the two objects. So the low pressure means lower pressure than the external pressure, the gravity, the average pressure. So low pressure isn't low by some, the negative isn't something special, it's just something less.
Positive. Minus times plus is minus. So I can do negative work if the two don't have the same polarity.
Yeah, so what I just said is sort of garbage because clearly I'm talking about it's lower pressure than the average. So in the gravity example, gravity is the average pressure surrounding everything. And two things to be repulsive have to have enough more pressure inside than is on the outside. So more pressure than gravity is producing, pushing in. And if they have less pressure than gravity's pushing, then we call it attraction, but they're just pushed together. So it's lower than the ground or the neutral in the case of gravity.
I want you to convince yourself that if I didn't come along a straight line from all the way from infinity, but I came in a very crooked way, finally ended up at point P, at that point, that the amount of work that I had to do is exactly the same. You've seen a parallel with 801.
So he's not, like again, he's not paying attention to any of the practical real world facts that if you take a different path, you have to take calorie steps to do all of that. You will do work. You just won't be doing work for your project. So if your project's climbing a hill and you start to go sideways, the sideways isn't part of the project, so it doesn't count as work of the project because you're not really gaining altitude. So you only count the parts where you gain altitude as the work for the project. But again, it's not really real world. Just like in the real world, you don't overcome gravity by just equalizing the force. You have to do more than equalize gravity. You have to overcome it.
Where we dealt with gravity. Gravity is a conservative force. And when you deal with conservative forces, the work that has to be done in going from one point to the other is independent of the path. That is the definition of conservative force. The electrostatic forces are also conservative, and so it doesn't make any difference whether I come along a straight line to this point or whether I do that in an extremely crooked way and finally end up here. That's it.
Yes, I know. Well, I'm just saying this, the way he's saying this, I think it's just a wrong way to say it. Clearly, if you're pulling a spring, you can kind of understand if I pull the spring and then I start going sideways and I go this way and I go some different ways, I'm not pulling on the spring anymore. I'm just wasting time going sideways. And if I ever do go sideways and I have a point I want to reach, point A, point B, it's inevitable that if I go this way, I'll go back this way again. I mean, to get to point P, I always have to go back. I always have to undo anything off the straight line. So I'm inevitably going to undo it with opposite work, so to speak.
The same amount of work. Now, if we do have a collection of charges, so we have pluses and minus charges, some pluses, some minus, some pluses, minus, pluses, pluses, then you now can calculate the amount of work that I, Walter Lewin, have to do in assembling that. You bring one from infinity to here, another one, and you add up all that work. Some work may be positive, some work may be negative. Finally, you arrive at the total amount of work that you have to do to assemble these charges. And that is the meaning of capital U. Now I turn to electric potential.
All right, good, because I don't think that U stuff comes in handy much.
And for that, I start off here with a charge which I now call plus capital Q. Located here. And at a position P, at a distance r away, I place a test charge, plus q. Make it positive for now, you can change it later to becoming negative. And so the electrostatic potential energy, we know already, we just calculated it, that would be q times q divided by 4 pi epsilon 0 r. That's exactly the same that we have. So the electrostatic potential energy is the work that I have to do to bring this charge here. Now I'm going to introduce electric potential. Electric potential.
So the idea would be is you brought the charge to there with a certain amount of energy because it's repulsive. And bringing it closer would require more energy. But that's how much energy it took to make P that close to Q. And the idea is that represents a certain amount of pressure stored in between Q and P. So now their energy is still there. You've put it in there by forcing them together. I would argue the mechanism of putting it in there is the fact that there's force bouncing between Q and P. And now that force is bouncing at a higher rate than it would if it was at infinity. If it was infinity, it would be you wouldn't even know it was bouncing. It was bouncing so slow. Now you've made it bounce fairly rapidly, and that represents pressure. And it could represent more pressure than the ground neutral, or less pressure still.
And that is the work per unit charge that I have to do to go from infinity to that position. So Q doesn't enter into it anymore. It is the work per unit charge to go from infinity to that location P. And so if
I don't get this unit charge concept at all, so I can't say much about it. Again, what you've done is stored the work as energy in the force bouncing back and forth. Maybe that's what he's talking about, but I don't know.
it is the work per unit charge that this little q disappears. And so now we write down that V at that location P. The potential, electric potential at that location P is now only Q divided by 4 pi epsilon 0 R. Little q has disappeared.
So the potential is just the distance. So the R just represents the distance, and the potential is a standard. It's essentially a constant. And the only thing that matters other than that is it's like a gravitational argument, is how big the Q is. So obviously it takes more, the bigger the Q, which means in a sense the more force that's bouncing, the more ping pong balls. The bigger the Q, the more ping pong balls. That means the more force you're creating when you get close to it. So it's, yes, so it's perfectly consistent with that analogy.
It is also a scalar. This has unit joules. The unit here is joules per coulomb. I have divided out one charge. It's work per unit charge. No one would ever call this joules per coulomb. We call this volts, called after the great Volta.
Which makes so much more sense. Obviously, volts seems to really so much better than that joules per coulomb thing, which again isn't very understandable. So yes, so then we have volts, which is the pressure, and it's the pressure times the volume, how much of the stuff equals the watts, which would be the total energy. So speed plus volume equals energy.
There's a lot of research on this, so we call this volts. But it's the same as joules per coulomb. If we have a very simple situation like we have here, that we only have one charge, then this is the potential anywhere, any distance you want from this charge. If R goes up, you're further away, the potential will become lower. If this Q is positive, the potential is everywhere in space positive for a single charge. If this Q is negative, everywhere in space the potential is negative. Electrostatic potential can be negative. The work that I do per unit charge coming from infinity
just means the volts goes in the opposite direction, obviously. So if they're attractive, the voltage is, you're the voltage, you're the thing of low pressure being pushed. The low pressure is in front of you instead of behind you. Simple way to say it, I suppose. The high pressure
would be negative, if that's a negative charge. And the potential, when I'm infinitely far away, when this R becomes infinitely large, is 0. So that's the way we define R0.
And which is arbitrary. So again, it's like a lot of mathematics has this point where you have to use, you know, the numbers just keep going up. And you know that it's sort of insignificant, but it's not really going to be 0. So it's, you're just saying we have to quit somewhere. You could quit at some more rational number and just say, well, yeah, we're not going to bother with, you know, stuff we can't even measure. It's so insignificant.
So you can have positive potentials near positive charge, negative potentials near negative charge, and if you're very, very far away, then potential is 0. Let's now turn to our Venn graph. It's a hollow sphere, has a radius r, about 30 centimeters, and I'm going to put on here plus 10 microcoulomb. It will distribute itself uniformly. We will discuss that next time in detail, because it's a conductor. We already discussed last lecture that the electric field inside the sphere is 0, and that the
So again, 0 in being net 0. So there is field, it's just that it's always positive and negative in equal proportions in any location, so it adds up to 0, but there's still activity in there that would be considered of electromagnetic nature. It's like me saying I can put two magnets of the opposite polarity, you know, with something in between, and that in between thing is just staying in there because it can't decide. Wouldn't be quite right to say there's no field there or there's no energy there. There's clearly energy there, and it's probably going to twitch being in that opposing field, especially if my hands are holding the magnets. My hands are going to move a little bit, so it is moving. It is you know, 0 is just not fair, that's all. Just a
electric field outside is not 0, but that we can think of all the charge being at this point here. Plus 10 microcoulomb is all here, as long as we want to know what the electric field outside is. So you can forget the fact that it is a sphere. And so now I want to know what the electric potential is at any point in space. I want to know what it is here, and I want to know what it is here at point P, which is now a distance r from the center. And I want to know what it is here at a distance little r from the center.
Well, obviously we already answered the question to the little r, but continue. Nothing.
So let's
plus minus equals 0. But it wasn't a nothing equation. The equation wasn't 0 plus 0. There were real numbers in the equation. They were just opposite numbers.
first do the potential here. The potential at point P is an integral going from R to infinity. If I take the electric force divided by my test charge Q dot the R. But this is the electric field. It is force times distance is work, but it is work per unit charge. So I take my test charge out. And so this is the integral in R to infinity of E dot dl, the R, sorry. And that's a very easy integral, because we know what E is. The electric field, we've done several times.
I would argue that it should be even easier than that, because if you know what the voltages you created, you should be able to do point P, just by the R squared rule, but whatever.
Follows immediately from Coulomb's law, and so when you calculate this integral, you get Q divided by 4 pi epsilon 0 R. which is no surprise because we already had that for a point charge. So this is the situation if r, little r, is larger than capital R.
Little r is larger. Okay, so r is this total distance. Capital R is the radial distance. So again, I would suppose, I would argue that if you could establish what this center would be, if see, they measure the voltage based on what it is on that outside piece of metal. So that does create a intuitive problem. I mean, what relevance does the radius have? And I mean, calling this an R that just confuses things. What's the dr? Oh yeah, that's the little distance you cut out of it. Oh, forget it.
Precisely what we had before. We can put in some numbers. If you put in R equals R, which is 0.3 meters.
So that's the surface of the Venn diagraph.
And you put in here the 10 microcoulomb and here the 30 centimeters, then you'll find 300,000 volts. So you get 3 times 10 to the 5th volts. If you take R...
So the surface of it has that voltage. And that's... I just don't really know how they have the assumption of some kind of voltage. It just doesn't charge up to that voltage automatically. So I don't know where he got the... Yeah, I don't know where he got that from. You could have 50,000. You could have different voltages on that surface depending how much you crank the machine up.
Equals 60 centimeters. You double it. If you double the distance, potential goes down by a factor of 2. It's 1 over R. So it would be 150 kilovolts. And if you go to 3 meters, then it is 10 times smaller. Then it is 30 kilovolts.
All right. So essentially he's creating a monopole of charge. And so this monopoles of charge go by the R rule instead of the inverse square rule. So good to know.
And if you go to infinity, which for all practical purposes would be lobby 7, if you go to lobby 7, then the potential for all practical purposes is about 0. Because R is so large that there's no potential left. So if I, Walter Lewin, march from infinity to this surface of the Venn diagram, and I put a charge Q in my pocket, and I march to the Venn diagram, by the time I reach that point, I have done work. I multiply the charge now back to the potential. That gives it work again, because potential was work per unit charge. And so the work that I have done then is the charge that I have in my pocket times the potential, in this case the potential of the Venn diagram, if I go all the way to this surface, which is 300,000 volts. If I were a strong man and I would put 1 coulomb in my pocket, that's a lot of charge, then I would have done 300,000 joules of work by just carrying the 1 coulomb from lobby 7 to the Venn diagram. That's about the same work I have to do to climb up the Empire State Building. It's the famous mgh, my mass times g times the height that I have to climb.
So we could assume that whatever this Coulomb thing is, it's got to be pretty gigantic, because obviously you can walk right up to a Venn diagram without much trouble, so you don't have too many coulombs of charge that you're carrying.
So I know how the electric potential goes with distance. It's a 1 over R relationship. Now I have arrived at the Venn diagram. I am at the surface with my test charge. And now...
So in this conversation, we're basically talking about the pressure. So we're talking about how much pressure is between electrons. So the analogy fits. The Q1 and the Q2 are basically just thought of as electrons. We're in the atom. How much pressure do the electrons have if they are being pressurized by these forces? And that's essentially what we're talking about here.
I go inside. And I slosh around inside. I feel no force anymore.
So I'm just pointing out that we're talking about its pressure and the relationship to pressure, and then the relationship that pressure causes polarization, two subjects. So I'm basically arguing that there's a neutral pressure, the ground pressure of an atom. Then you can, when the atom's expanded a little bit, there's less pressure between the electrons. When the when the ring is contracted, then there's more pressure between the electrons. So this would be your high pressure. This would, out here, would be your low pressure atom. And this force is doing that pressurization. Now, as it does that, it passes through the neutral. So there's a neutral ring, and then there's a big ring, small ring. You pass through the neutral. That's the ground. So everything less than neutral makes a negative ion. Everything plus is a positive ion, blah, blah, blah. So you're creating monopoles of charge. And those monopoles of charge, big atom, little atom, can be arranged in a substance next to each other and cause magnetism. Like a bunch of little magnets create a bigger magnet.
There's no electric field inside. So as I move around inside, I experience no force. That means I do no work. So that means that the potential must remain constant. So the absence of an electric field here implies that the electric potential everywhere is exactly the same. Inside is the same as on the sphere. Because no further work is needed in marching around with a test charge.
So he's just implying that there's 300,000 coulombs or whatever, or UCs of, well anyway, there's 300,000 volts inside, which may or may not be correct. The point is that it's in a form where it's neutral, in that you're hit with 150 negative and 150 positive from every location, so it really can't add up to that. So in a sense, it really can't be, but whatever. Let's just play along.
And so for this special case, I could make a graph of the electric potential versus R, and this is then the radius of the Van de Graaff, and that would be a constant all the way up to this point, and then it would fall off as 1 over R here. And for the
So, I mean, as a practical matter, he's already pointed out that if he puts a ball inside of that ball, he's not going to be able to pick up any charge. So this is sort of, I don't think, correct. It's still zero because it's zero. There's no difference. So I guess he's claiming that in a Van de Graaff, there would be charge inside that's equal to the surface charge, and would have to be equal to the point charge in the center or something. I don't even know how that makes sense, frankly. Still can't do anything with that. So I'm not saying you won't pick up charge, because obviously the inside of the Van de Graaff is where all the charge is actually the atoms that have been pressurized are being pushed right onto the surface of the Van de Graaff and causing the pressure that's creating the voltage. So you're certainly going to get hit by those atoms and start picking up charge.
The numbers that we have chosen, the potential at the maximum here would be 300,000 volts.
What the Van de Graaff is basically doing is it's creating friction at the bottom. By doing that, creating pressure. It pressurizes atoms. The atoms are in a conductor. They move the charge up, and then they irradiate it to the inside of the sphere. There's a wire connecting it. It's a conductor.
Just as when you look at maps, where you see contours of equal height of mountains, which we call equal altitudes, here we have surfaces of equipotential. And if you had a point charge, or if you had the Van de Graaff, these surfaces would be concentric spheres. The further out you go, if the charge is positive, the lower the potential would be. It would be nicely spherical surfaces. Suppose now we had more than one charge. We had a plus Q1 charge, and we had a minus Q2 charge, for instance. And you're being asked now, what is the potential at point P? Well, now the electric potential at point P, Vp, is the potential that you would have measured if Q1 had been there alone. You have to add the potential that you would have seen if Q2 had been there alone.
So this again is the superposition principle which basically just says the two forces don't interact with each other in any way. So you'll get hit by whatever Q1's producing, you'll get hit by whatever Q2's producing, and the two Q's won't screw each other up much. But in practical reality, if Q1 and Q2 are magnets, for example, dipoles, they will mess with each other. And I suppose even regular charges could subtly change the composition of the charge on their surfaces based on the fact that when they get together they'll deform in their shape, and if they deform in their shape then the pressure will be different because there won't be any more spherical symmetry. So it's not technically precise, it's generally true that it doesn't matter what the other charges are doing, but it can matter.
Just adding work per unit charge for one with work per unit charge of the other. And if this is negative, then this quantity is negative and this is positive. So when you have configurations of positive and negative charges, then of course, depending upon where you are in space, if you're close to the plus charge, the potential is almost certainly positive, because the 1 over r is huge. If you're very close to the negative charge, again, the 1 over r of this little charge will dominate, and so you get a negative potential. And so you have surfaces of positive potential, and you have equipotential surfaces of negative potentials, and so there are surfaces which have zero potential. And they're not always very easy to envision. But what I want to show you is some work that Maxwell himself did in figuring out these equipotentials. And so I have here a transparency of publication by Maxwell. You see a charge, let's assume it is +4 and +1, it could be -4 and -1, but let's assume they're plus. And you see the green lines, which we've seen before, which are the field lines. Don't pay any attention to the green field lines now. The red lines are equipotentials. And
so he's saying ignore the radial lines and just pay attention to the round and the green round lines. And the round lines are somehow a description of where, as these are both the same charge. No, these are two things of opposite charge. No, same charge, yes. Their lines are going away from each other. So, I don't know what... well, anyway. Continuing.
You have to rotate them about the vertical because they are, of course, surfaces. This is three-dimensional. I have not drawn all the...
so he drew on Maxwell's images. That's why I'm saying the red lines are a little sloppy. So, yeah, it didn't seem like a Maxwell publication to me. Okay. So he drew on Maxwell.
Equipotential surfaces in red because they become too cluttered here. But I've tried to put most of them in red. Since this charge is positive and that charge is positive, everywhere in space, no matter where you are, the potential has to be positive. There's not a single point where it could be negative. If you are very far away from the +4 and the +1, then you expect that the equipotential surfaces are spheres, because it's almost as if you were looking at a +5 charge. So it doesn't surprise you that when you go far out, that you ultimately get spherical shapes. When you're very close to the +4, they are perfect spheres. When you're very close to the +1, they are perfect spheres. But then when you're sort of in between, neither close to the +4 nor to the +1, they have this very funny shape. It reminds me the shape of this balloon a little bit. Sort of like this. You see? And there's one surface which is most unusual.
The catch of this is that shape, it doesn't mean anything travels those lines. It means exactly the opposite. Things will be pushed another positive charge. If these were two positive charges, another positive charge would be pushed away on a parallel to those curved lines. So the curve of the line, whatever parallel is to the curve, that's the direction the test charge would head off in if you placed it there. So that's all these lines are really good for.
Equipotential surface, which here has a point where the electric field is zero. It's sort of like twisting the neck of a goose. You get something like this. And so you have here a surface which...
I don't think too many of us have that as a very good analogy. I guess he grew up twisting the heads off of geese. You know. I don't know. Yeah, I don't. Yeah, I don't know if this is nothing but a coincidence that there's some parallel.
There's a point here, and it is exactly at that point where the electric field is zero. That does not mean that the potential is zero. Of course not. The potential is positive here. If you come with a positive charge from the lobby 7 and you have to march up to that point, you have to do positive work. You have to overcome both the repelling force from the +4 and the repelling force.
Well, you have to overcome all the other lines to get there. So you have to go through all the other lines to get to that point. But once you're at that point, nothing's going to bother you as long as you stay exactly there.
From the +1. But finally, when you reach that point, you can rest, because there's no force on you at that point. That's what it means that the electric field is zero. It does not mean that you haven't done any...
So again, there's plenty of force on you. It's just yin and yang. It's just that you're being pushed by both things into both things. So you're exactly right between the two things. And nothing in the real world can ever do that. It always veers off because that's a tiny point. The center of gravity to the center of gravity to your center of gravity all have to be in a perfect line. And just being a little bit off that line and you'll start moving. So it's not exactly an achievable point. If it was easy to achieve, we could just place magnets in these arrangements and they would stay there really easy. We usually have to do something to force them to stay within some sort of boundaries, because as soon as they get outside those boundaries or they flip over or some other thing, they'll break whatever tension you can create. It's that sensitive. But in the real world, things can be that sensitive. Atoms and stuff like that.
Work. So never confuse electric fields with potentials. I want to draw your attention to the fact that the green lines, the field lines, are everywhere perpendicular to the equipotentials. I will get
So that's what I just said before about going off parallel to the, perpendicular to the lines.
Back to that during my next lecture. That is not an accident. That is always the case. Now, Maxwell shows you something that is a little bit more complicated. Here, he calculated for us the equipotential surfaces. The red ones are the surfaces. Again, you have to rotate them about the vertical to make it three-dimensional. And now we have a -1 charge and a +4. And so whenever it is red, the surface, the potential is positive. And whenever I have drawn it blue, the potential is negative. First, if we were very far away from both the +4 and the -1, you expect to be looking at a charge which is effectively +3. And so if you go very far away, for sure, the potential is everywhere positive, and you expect them to be spherical again. If you look here, you're very far away from the +4 and the -1. Indeed, this has already the shape of a sphere. So that's clear, that the +4 and the -1 far away behave like a +3. If you're very close to the +4, you get nice spheres around the +4, positive potential. If you're very close to the -1, notice that the blue surfaces are almost nice spheres, but now they're all negative.
That makes this a little bit complicated is the choice of your test. If you put a test thing in, yeah, I'm not sure. If you put a minus charge in from the furthest red line, I'm not quite sure if it goes to the 4 or the 1, but anyway, it doesn't matter. Depends on how big the test charge is, so that's the whole problem. Put a +3 in there, everything gets messed up, so yeah, you have to use a neutral charge.
Negative, because you're very close to the -1, so a negative potential. There is here one surface which now has zero potential. It has to be. Because if you're negative potential close to the -1 and you have positive potential very far out, you got to go through a surface where it's zero. And so there is here a surface, I still have put it in blue, which is actually everywhere on this surface, the potential is zero. Is the electric field zero there? Absolutely not. Electric field should not be confused with potential.
So again, the attraction to one and the repulsion of the other equal out. But that surface, it wouldn't be a surface, because on the other side they wouldn't be equal. So I don't know why he said on that surface. There's a point on that surface, 1 point, 1.
What it means is that if you take a test charge in your pocket and you come from infinity and you walk to that surface, that by the time you have reached that surface, you've done zero work. That's what it means. The potential is zero.
So you've walked up as much hill as you've slid down. So if you count sliding down as a compensation for walking up, you've done as much work.
There is here one point, which we discussed earlier in my lectures, where the electric field is zero. The potential is not zero there. The potential is definitely positive here. Because here was the zero surface. Here is already positive surface. And this is a positive surface. So the potential is positive. However, if you reach that point, there's no force on your charge. So that means electric field is zero.
All right, so when he's saying that one has the surface that's zero, again, you can see there's only one red line you go through, one blue line. So, I mean, you're going through two of the same amount of force. So you go up the hill and down the hill. So you're at the same point you started. That's different than the point where both attraction and repulsion balance and you have the zero. So the E equals 0, 1, the higher point, is the same as the one was inside when you had two repulsive. So it's just it's the same point, but when you have the opposite charges, it goes outside both the charges, obviously. So it's being, a positive charge would be pulled by the 4 by the same amount of, the positive is the 4, so a negative charge would be repelled by the 1 by the same amount it's being attracted by the further away 4. But this always assumes too that charges don't block charge, which in atoms I think they could do. So anyway, I mean, electrons could block the force of the proton, and it wouldn't matter how far away the proton was if it's obscuring it, like a planet obscures this light that comes off the sun. If it's blocking it, the radiation, it's blocking it. So, and I think in a practical sense, that's how it really works.
But it's not so easy, of course, to calculate these surfaces. Maxwell.
Okay, so I think it's a good enough place to stop, and we'll pick it up next time and such. What am I looking for? I'm looking for this. Yeah. So maybe I'll pop some of this writing in here somewhere just for the hell of it. In the description, there, there's just one force. There's certain bullet points regarding how I think this all works in terms of what can be stated as the causes and the effects. And so I'll do that. Put it in the description somewhere at the bottom and such. So till next time.